So, Jara, do we have everybody in now?
Yeah, we have most of them. I think the rest will be joining. So,
Uh,
you
okay,
know,
okay,
keep
okay, that's
joining.
fine.
Just so we
Um,
can allow those online to join us.
okay, okay, that's fine. So, good evening,
Okay,
everyone. Okay,
uh,
Jara, go ahead.
okay.
Go ahead. Mm.
Okay, so good evening, everyone. It's a pleasure to welcome you again to another fantastic session as part of our ongoing SP Port Harcourt section Petroleum Engineering Industry Experience Bootcamp. My name is Gerald Ihediloni, as you know, one of the organizing committee lead for the Bootcamp and also co-founder for Excel for Energy, and it's my pleasure to be moderating this session again. It's a, like I said, it's a fantastic session. I call it a midweek special because it's been specially organized for you, the participants of this program, just to give you, that extra bit of skill set, using Microsoft Excel for petroleum engineering workflows and analytics to improve productivity. So, just another area, to learn and improve your skill sets as part of the overall learning in this program. And of course, we have fantastic speakers brought to you today. No other person than Dr. Pringle Egbe, section chair for the SV Port Harcourt section. Also the first person to teach me and make me interested in Microsoft Excel and teach me up to the level I am today. So it's a pleasure to have you come on here today to kick off this session. Um, I'll just do the honors of introducing him. I know some of you already know this profile, but to observe protocol, Dr. Pringle is the President and Strategy Director at Western Point Energy Services, an experienced oil and gas computing engineer with over 13 years experience in Europe and West Africa, focusing on digital oil field solutions and data systems. He's a renowned expert in business process optimization, digital solutions, and workflow automation. He holds a bachelor's degree in electrical and electronics engineering from the University of Port Harcourt, MSc in oil and gas computing from Robert Gordon University, UK, and a PhD in engineering management from the University of Port Harcourt. He has been an industry lecturer at the Institute of Petroleum Studies at the University of Port Harcourt and Center of Excellence in Geosciences and Petroleum Engineering at the University of Benin. He also founded Excel for Energy, a free Microsoft Excel learning community for energy professionals. He's a regular short course facilitator, as some of you may know, at the SP Annual International Conference and Exhibition, where he teaches the short course on using Microsoft Excel and macros for productivity and workflow automation, as well as its practical application in oil and gas for modeling, data analytics, visualization, and economic analysis. He has, lectured quite a lot of us, young professionals, as well as senior professionals in, Microsoft Excel and its application in the energy industry. And, that has been a tremendous skill set for a lot of us, using that and applying that in our day-to-day tasks in the industry. So on that note, I'll just open the floor for Dr. Pringle to kick off the session. Please, a round of applause. Yeah, I see some of you already clapping. Please, a round of applause for our section chair as he kicks off the session.
Okay, good evening, everyone. Okay, Jara, confirm you can hear me.
Yes, yes, I can hear you, sir.
Okay, just to kickstart the section, Israel, please, can you share our slide?
Okay, okay. Yeah, give me a moment, sir.
Okay, hello, Israel.
Oh, sorry, I've not been hearing me. Sorry, sorry. So I'm sharing my screen now. I can't. I have to replace you. I have to replace that. So there, I'm sharing my screen. So just confirm you can see my screen now.
Yes, yes, we can. We can see it.
Okay. Yeah.
Okay, good evening, everyone. Just to begin this section, I feel it's a privilege for me to take this course alongside my mentees, and it's just like a professor having some PhD students around him. I was thinking, who is the next PhD student I'll take this course while I just watch him. So I know that I have Jara this year too, but Jara cannot take it because they were moderating this section. So on that note, we'll just introduce the course. Then I will let Israel run over the course while I watched him because you need to train people that are replaced in the industry. So Israel is one of them. So part of this course is part of our initiative from Excel for Energy, which Jara Israel happened to be a co-founder too. So I happen to be the founder of Excel for Energy. Israel, we have Israel as co-founder. We have Jared, Samuel is also in here for Excel for Energy. So the strategy is any of us can take the course with the same slide. This is slide we use for SP short course. So on that note, I'll let Israel take the course. Then I'll come in and also do some summary in some section. So while we start, so Israel, I would like you to take the course from the slide from the first slide. Then I'll just let you know I'll come in to take it. But let me just see how it goes. So Israel, uh, you can take it from here.
Okay. So good evening, everyone. Please confirm you can hear me very well.
Yes, it's very loud and clear.
Okay, thank you. Okay, so tonight we're going to just have a small session that we believe will be very helpful for everyone here, given what we are doing, the bootcamp we are currently going through, and probably to be useful in your future endeavors. And the normally teaching Excel would be very voluminous, and so we have tried to streamline it to really focus on something specific here today. Um, so I'm just going to reshare my screen for us to start all that. So let me share this. All right. So confirm you can see the new screen up here. Gerald.
Yeah, everyone can see your screen.
Okay, cool. So today, right straight into it, our first focus point would be handling decline curve analysis and curve fitting. Now, um, we are going to try to make sure the course is easy or the session is easy to follow with everyone. And so for that reason, I'm going to send a document to the group chat. And so everyone can download so they can probably follow along so it's not lost on you while you're going. Some of you can decide not to follow along and just pay attention. You can decide to take notes. If that's your forte, that's no problem. So do I have permission to share my file with on the group chat, Gerald? Or should I just share it here?
You can drop it on the group, maybe at any time. It works.
Okay. Okay, so let me just get the file out here and then share it to everyone. And this is really just so that everyone can follow along as we work. Okay, while I do that, let me see. Okay. Okay. All right. So just to confirm, I'm sharing it to the group chat called Section 103 and CCL Petroleum Engineering Bootcamp for everyone to have this. Okay. All right. So let me get right into it. Decline curve analysis and curve fitting. Now, as production technologists, one of the things you would want to do, or you would most likely do most of the time, is production forecasting, considering the conditions you're currently working at. From what I understand for this bootcamp and the field development project you're working on, it's a special condition whereby you are currently going through some form of intervention, and then you want to probably see your behavior as time goes on for all the different wells that you are working with. And in this case, you would need to perform or utilize some tools to perform some form of forecasting. And apart from the regular diagnosis, surveillance, and performance monitoring that you would do, uh, that stuff like this would also come in. And so decline curve analysis, basically, I'm just going to use this cartoon to explain what's really happening. Uh, Regularly or normally, as you know, as you produce, your pressures would reduce, your reservoir pressures will reduce. It will be more difficult for you to get volumes to the surface. And so the volumes that you get will be reduced at the surface. And in that case, you would want to know where you're going to get to the end point of your production, something that people can call your economic limit, and then basically use that to plan a lot of things. The economists would need that. Even the reservoir engineers would be paying attention to what's happening there. And so in that case, what decline curve analysis basically says is, let's look at this historical behavior of our data and use that historical behavior to tell ourselves what's going to happen. And considering the behavior that oil and gas reservoirs have, we noticed that, or engineers noticed that we could have either an exponential decline, a hyperbolic decline, or a harmonic decline. Those are things that I believe most of you would know as petroleum engineers here. But because the disciplines are diversified, I have to give this little background here. And so in that case, what you really need to do is develop equations or work with equations that can help you define the previous behavior and then use those equations to forecast what's going to happen in the future. And this is very similar to every other forecasting problem that we can have, where no matter what it is, a regression problem would probably have you trying to understand the past to predict the future. And the good thing about decline curve analysis is that you have the good thing about decline curve analysis is that you have um, a a supervised regression such that you can create a white box model out of what is happening here because you have already defined equations. And so apps came up with a couple of equations. In reality, these are just general equations for um, exponential decline of most things, or hyperbolic decline or harmonic decline, but we can adapt them to the way the reservoir behaves. And so apps came up with these equations for us to use when we want to try to model the behavior of our reservoir for the future in terms of production forecasting. And so we have these equations that are made up of your production information, your time information, your decline rate information, and your curve behavior information. And so you see for the three of them, you have where it says where B is equal to something, where B is equal to 0, or where B is between 0 and 1, or where B is just 1. And I like to just mention, I like to, for simplicity's sake, I like to call B a curvature factor. Um, and we'll see that kind of behavior when we start working in Excel. A curvature factor would tell us, are we working in an exponential phase, or working in a hyperbolic phase, or working in a harmonic phase? And then we have the decline rate factor, or the D. Now, for the decline rate factor, that is basically what is telling us by how much are we losing our production ability. And that's where the D comes in, the DI that you see on the screen here. So this DI here basically tells us, am I reducing my production by 5%? Am I reducing my production by 2% every year? Am I reducing it by 1% every year? And so for a case like exponential decline, the decline rate, or the decline factor, let's call it the decline rate factor, really is the only defining change that happens in terms of what helps us predict our production. It's different from what we have in hyperbolic and harmonic, where we also see that B is defining how the change happens as time goes on. And so um, the other information that I mentioned were the production information and the time information. And these ones are important in the sense that what you're trying to do is you're trying to determine production at every point in time. So that's where your Q with brackets T comes in. Your Q in bracket T means what is the production I have at time T. And the way this equation is set up, it works with days. And so on day X, what is the production I have? On day Y or on day T, what is the production I have? And this is dependent on my initial production rates and my decline rate, or my decline factor. And then when I'm working with other types of conversions, or when I'm working with other types of declines like hyperbolic or harmonic, I also need to consider my B, or my curvature factor, which I mentioned for simplicity's sake. And really this is what decline curve analysis plays around with. These equations, these three equations, how do we use these equations to predict Q? And so you would notice from here that we can know what we can know what QI is, considering that QI is just our initial production at a particular time. We can know what T is, considering that T is just the time that we currently are in days. But sometimes we are not, or most times we're not really going to know what D stands for. And because there is an unknown, it means there is a solution that we need to get. There's something to solve for. In a case like hyperbolic or harmonic, we have an unknown of B as well as unknown of D. And this means that we have a case where we want to solve using more complex methods. And according to mathematics, when we are solving things with multiple unknowns in an equation, we need to start employing some form of simultaneous equations solution. And really, the idea of needing simultaneous equation solution is where curve fitting started to come in. And if you look at curve fitting from the base of it, it's like, okay, I have this equation. I want to know what my unknowns are so that I can predict more with this equation. How do I know what those unknowns are, considering that I have some knowns? When I show you the data, I'm going to explain this again. But basically what I'm trying to say is that with this, we can bring out a classic case of curve fitting in petroleum engineering to help predict or to help forecast something that we need. And so today, for this first session, we're going to work with all the things that you need to consider when you're trying to develop or when you're trying to handle curve fitting. And for this session, we're going to work with Solver. I don't know. I don't know if we have worked with Solver a lot, but for this session, we're going to see how we can use Solver as a concept to handle our core fitting. In this case, we are just trying to get to minimize something. And when we get there, I would show. And then when we perform our predictions, we would also want to see some form of cumulative forecasting, because it's not enough to just forecast our production at time X or time Y. We would also want to know how much production or what our cumulative production would be, what our EUR would be, our ultimate recovery, what our reserves are. And so we're going to also employ these equations. Say, okay, so with this, I'm just going to jump right into Excel. I believe that at this point, everyone has the document I sent on the group chat so you can follow along. So we're just going to jump right into Excel. We're going to start setting up our sheets. For this case, we're going to use VBA, we're going to use Solver and regular basic functions. So I'm just going to stop sharing my screen now and bring up my Excel workbook. Okay, here's Excel. Okay. All right, so please confirm you can see my screen.
Yes, we can.
Okay, thank you. So for this example, we have this simple data. Basically, what's happening with the data, we have production starting from 31st. We have production records starting from 31st of January 2014, where we began this production. And then it started to decline. And really, it declined until the date that we currently are, assuming that we are in May of 2016. And so our most recent production information was from the 30th of April 2016, telling us that we had a production rate of 470,000 barrels per day. Okay, and for 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 this, what we're really trying to do is we're trying to look at this data here, and then we're going to create our forecast. But before creating our forecast, we need to determine the other parameters that I mentioned from the slides. So I'm just going to get the slide, the formulas from the slides so they can help us here. Okay. All right. So for QT is really what we're trying to forecast. And in this section or in this segment of the worksheets, you can see that I have my production rate for forecast, and that's QT. QI is really, for this situation or for this scenario, our initial production on the 31st of January 2014. Our D, we do not know yet. The cell is empty. Our T, we can tell as the time in days. We're just going to compute that very quickly. And then for cases that we cannot foresee yet, we also have to consider B, which is here, because we can't tell for sure what kind of decline we currently have. And so we are also going to keep provision for our curvature. Okay, so back to the explanation I was making before. Okay, before I do that, let me just compute my days. This is my first day, so it's just going to be 0. I'm just going to create my other days. And I'm just going to use a very crude method to get my number of days. So this has to be stagnant because I'm referencing my initial production date. So I'm just going to drag this down to whenever. And so I have 2060 days in total that I'm trying to work with in terms of my forecasting. But let's ignore the number of days for now. Let's really just focus on this segment that I have my data. Now, following the laws of regression, if you have your X and you have your Y, you can find your unknown value, given the regular equation of a straight line, which is Y is equal to mx plus c. In this case, m is an unknown, c is also an unknown. If you have your Y and your X values, you can create a regression and fit your curve onto that so that you can know what your M and your C are. So in this case, our unknowns are the D and the B. We're going to follow them one by one. And our knowns are the Q, and the T. That is the production rate, that's the QT, and the time in days, that is the T. So what I'm going to do now, I'm going to create Excel functions using VBA that we can call whenever we want to do our forecasts. And so I'm using this opportunity to also show us how to use VBA, play around with VBA, create simple stuff with VBA that can just help you get things done on Excel. And so what I'm going to do on VBA, first of all, I'm going to create a function that helps us perform these forecasts using these parameters here, the Q, the D, the T, just as I have here, the Q, the D, the B, and the T. In this case, let's ignore this T for now. Sorry, I need to read that one out. The T that we're focusing on is this T, not this T. I'm going to come back to this T at the end of this session. Okay, so considering these values, let's create our Excel function to, so let me hide this, please. Hide floating panel, thank you. So Excel VBA, for some of us that have never used Excel VBA, I'm just going to demonstrate how you can get Excel VBA working on your system. This method I'm about to show works or checks out for Excel versions from 2013 upwards. For 2010, slightly different, but it's mostly the same, mostly similar. So if you want to activate this panel or this tab, sorry, I keep getting, can you remove me from being the co-host so that my floating panel doesn't keep coming up? Christian.
Yeah, I've done that.
Okay, thank you. Okay. So this is a tab in Excel, and by default, this tab will not be shown on Excel, and so you have to intentionally bring it out for you to access for you to access Excel VBA or VBA on any office tool, like actually. So what just happened? So to do that, you can go to options, go to file and go to options. Under options, all you have to do is to go to customize ribbon. person can favor mute their mic. Okay, thank you. So all you have to do is come to your options, Excel options menu, and go to customize ribbon. On the right side, you're going to see these main tabs. These are the tabs that are going to show up here whenever you open Excel. And normally your developer tab will not be checked. So all you have to do is to just check it, and then you get your developer tab activated after you click on OK. So I have my developer tab here. I have my data here, my X and Y values. And I have this chart here that I'm going to be using to monitor what I'm doing. What I'm going to do now is to get into VBA and get my function set up. So to open your VBA developer environment, all you have to do is click on this Visual Basic option here under the developer tab. And when you do that, you're going to see something that looks like this. It might not be exactly like this, but it's going to look like this. It's going to have the name of the file that is open. It's going to have MS Excel objects. It's going to have your sheets and this workbook. You might not have these modules here. That's not a problem. All you have to do is to right click on the sheet, and then from insert, you can click on module. The moment you click on module, you're going to see this folder like thing pop up, and then your modules also come out here. I like to use modules to create my code, but okay, let's not get into that because that's a different okay. So let's get the function started. So like I said, the functions we're going to be creating are functions that we're going to need while forecasting. We're going to call by ourselves while forecasting. Now, in reality, you can decide to type in your functions by hard-coded inside right there in Excel. That is also allowed. But I'm using this opportunity to show you how to work with VBA. Very simple demonstration here. So the first thing that we're going to do is we're going to have our decline forecast information, decline forecast function, because remember, we're trying to do a regression, a curve fit. So this equation that I'm basically trying to do is an equation that will help me. I'm so sorry, please. I didn't think of the fact that this is a new window. Can you see my VBA window here? Please help me confirm.
Yes, Israel, I can see your VBA window.
Okay, cool. Okay, thank you. So, okay, so let me just get back into it. Because remember, what we're trying to do is we're trying to tell what is our production rate here, considering that we have these knowns, so that we can use this to get our best possible values for DI and B. So I'm going to write the function here, and the function is basically going to be these three guys here. I said these three guys, but in reality, it's just going to be these two guys because this guy and this guy are the same functions. That's hyperbolic and harmonic. They're basically the same equation. The only difference is that in hyperbolic, B might not be equal to 1, but in harmonic, B is always equal to 1, and so the B component of it just disappears. And really, the exponential function is just another form of the hyperbolic function, but it's handled using calculus. It was derived with some calculus rules because of the behavior when you consider that b is equal to 0. Okay, so to write a function in Excel, you have to start with the keyword function. So I'm just going to type this now, function. And the function I'm trying to do is the function that forecasts my decline. So I'm just going to call it function forecast decline. I'm just going to write forecast decline. Now I can start going into all the rules of writing things in VBA, but on the very basic level, I cannot put a space here. If I put a space here, there's going to be a problem, and you see. It tells me there is a compile error because at this point where it saw the space, it expected that that's the end of a statement. And so that is one rule that you can just keep in your head. When you're declaring function names, variables in VBA, you can't work with spaces. So if you have a long name to use, just put all of them together. Or you can use something like an underscore to separate them. But I'm not using an underscore in this case. I just want it to be this way. Now, for my function, every function that we work with, whether we like it or not, would have arguments. Your arguments can be non-existent, your arguments can be existent, but every function would have its argument. If you look at Excel and you type a function is equal to sum, sum would have argument number 1, argument number 2. Those are the parameters that you need to mention when you're calling this function. So what I'm trying to do, I'm trying to create something like this, a function in Excel for myself. And so I have to find a way to declare the variables or the arguments, or let me say the parameters that would be required anytime I want to call that function. And so let me go back to my VBA. Where are you? So in this case, my function is basically the things that are in my parameter, my formulas, my decline formulas. And the things that are there are the QI, the DI, the B, and the T for my hyperbolic and harmonic. And then for my exponential, I have the QI, the DI, and the T. Okay, so in this case, what I'm going to do is I'm going to say QI as my first argument, then DI as my second argument, B as my third argument, and T as my fourth argument. Now, what this basically says is that anytime I call this forecast decline, I must provide all of this, right? Or if I don't provide all of this, I should provide some of it so that my computation can work based on what I define here. And so if I go back to Excel and I say is equal to forecast, I see that I have my function which I just created right here, forecast decline. And if I select that function and I come here to see the arguments for that function, I see my function arguments are QI, DI, B, and T. And so anytime I want to calculate my forecast, all I have to do is provide these values, and then I can get to where I want to get to. So I'm just going to quickly write the code now for this so that we don't waste much time. And the code is basically just going to be an if statement that goes between the exponential and the harmonic or hyperbolic. So if b is equal to 0, Then forecast decline is equal to, for exponential, where b is equal to 0, I have qi times exponential negative di times t. And that's for my exponential. And if it's not exponential, it should be the other function, which is forecast decline is equal to qi over 1 plus, let me check it, over 1 plus b dit all raised to 1 over b. 1 plus b times di times t all raised to power of 1 over b. Okay. And so this simple thing that I've created here just helps me define my function forecast decline, and I can then use it to forecast my production rate here. And so I'm just going to come here now and say equal to forecast decline, and then I'll define my Q. So my QI is going to be this. So I'm just going to make that stagnant. Then my DI is going to be here, which is my decline rate. Then my B is this, which is my hyperbolic factor. And then my T is the time I have here. And so I'm just going to click on OK for that. Sorry, I made a mistake. I'm supposed to put an end if here. So I'm just going to rerun that. Okay. So I have called my function that does my forecast on these my unknown values D and B. But in this case, I'm getting a 0. And that's because I have not yet defined my D and my B. And that is where the crux of the matter is. We're going to perform a curve fitting to define our D and B. So what I'm going to do, I'm just going to drag this down to the end of my known production. I'm going to, without formatting. And then I'm going to define my initial production. Then I'm going to define my DI as 0.05. Okay, let me take this away. And you see what's happening right here. As I define things, my curve starts trying to fit into my actual production. And so what I see that's happening here is that my DI at 0.05 tries to fit like this, and my B, let me say at 0.8, just a prediction, just an estimate, now tries to fit here. And so what's happening is that if I keep changing my DI and my B, at some point my curve is going to get into my actual rate. And that is where I am trying to really fit my curve into my actual production. And so what's happening, I can decide to continue going and say 0.005. Ugh, not good. I say 0.1. It tries to fit, and that feels good. So let me take this out of percentage, sorry, to number, right? And then I say, okay, 0.012. Oh, now I've overshot it. And then I can keep going like that forever and ever and ever, and I'm probably not going to get a proper fit for this, my forecast. And remember, if I don't get a good fit on this forecast, when I try to do my future forecast, I'm going to do rubbish. And I'm going to show you that right now. If I come here and continue my formula to the end without formatting, I would see that my forecast is quite low for my unknown data. And the more I keep changing my D and my B values, 0.1, the more interesting it gets. 0.03, 0.05. 0.05 is fair for me. So what I'm going to do now, I'm going to use solver to help to minimize the errors that I'm having between my forecast and my forecast and my actual values. So the dots here are my actual values and the line is my forecast. So I'm going to try to reduce the error between that. And I'm just going to use any, error metric system. In this case, the error metric system I'm going to use is just going to be an absolute error system, which just says that my actual minus, okay, let me just say my absolute of this minus this over my actual should give me an error. And so let me just take that down without formatting. And so what I'm seeing here is that my error is 3% on this point, 20% on another point, 0%, okay, 0% here, 20% here, about 17% here, and then it just keeps going like that. And for me to be able to minimize my error, I need to have a sum of errors so that I have a single point of calculation when I'm working with my solver. And when we get to that point, I'll explain how solver works. So in this case, I'm just going to create a sum of errors here. And I'm just going to sum all of these together. So what's happening here is that since I have this simple point, I can just minimize only this error. And then because the formulas, if I check this out, the formula is calling this. This formula is also linked to all these values. This formula is also linked to all of this. And so they create a network of functions whereby if I minimize one thing, all the other functions work together to get that point to its optimal value. Okay, so what I'm just going to do here is, since I have decided on my sum of errors, I know what I'm trying to get to, I'm just going to go back to solver now and actually run it. Run solver to minimize my error to get my curve to fit so that I can know my D, I can know my B, and I can create proper forecasts in this case. Okay, so I'm running out of time, so I'm just going to get this done quickly and I can get questions. I can get questions from you guys. So to get solver, you have to just go to the data tab and then you're going to see solver right there. But some of you might not see solver. And so to get solver to show on your system, in case you have not used it before, all you have to do is go to file. When you go to file, you go to options. When you go to options, you can go to your add-ins. Okay, what just happened? Okay, you go to add-ins and I believe it's a com add-in and click on go. Okay, that means it's an Excel add-in. So let me close this. Options, add-ins, Excel add-ins, go. Yeah, it's an Excel add-in. So when you open your Excel add-ins, you're going to see this solver down here. All you have to just do is just click on it and click OK. There are all other add-ins that come with Excel by default. The analysis toolpack and analysis toolpack VBA. For newer versions, you have the Euro currency tool, and then you have the solver add-in. You can also bring in your external add-ins. For some of you that would work with Monte Carlo simulations, you can have your add-ins like at risk. And then there are a lot of add-ins on the internet that you can use for many different things. But whenever you want to get your add-ins to work, all you have to do is come here and activate or deactivate. And so I have my solver already set up. And so what solver is going to help me do is it's going to okay. What solver is going to help me do is it's going to help me get this error to the minimum. Okay. So if I open solver, I have my information here. So I'm just going to close this. Now, I can't go into the nitty-gritty of optimization because I believe that most of us here have learned optimization. We are young professionals. We have probably learned optimization somewhere and done some things on it. So I'm just going to talk about Solver in itself. Now, Solver is just a tool that helps you run optimization considering functions and constraints. So if you have an objective function that you have defined, in this case, my objective function is the sum of errors that I have here. Okay. If you have your objective function that has been defined, you can define the variables that should change to get that objective function to where you want it to get to. And you can also define constraints on these changing variables so that you don't get absurd values. And I'm going to show you some values that can be absurd right here while we do this. So what I'm going to do, I'm going to set my objective function, my sum of errors. That is cool. I'm trying to minimize. You can maximize, minimize, or you can try to get a specific value, but here I'm trying to minimize. Okay. And the variable cells or the cells that should be changing can be either one of these three. But in this case, I'm going to focus on these two. So I'm going to highlight these two to change. Just stay with me. And you see why I'm doing what I'm doing. What I'm trying to say here is that, okay, change my curvature of this curve and change the rate of decline to help with the steepness of this curve. So your D helps with your steepness and then your B helps with your curvature. And so if you want it to be less steep, you change your D. If you want it to be less curved or more curved, you change your B. But in this case, we are changing these two cells. And then we're not going to touch anything else. We're on a non-linear basis, so we're going to use the geology nonlinear solving method. And then we're going to click on solve and see what happens. So as I've clicked solve, solver has told me, hey, I've gotten your solution. Amazing. It looks like my curve has been well fit to my data, even though my data looks really scattered. And so I can forecast I can actually give a reliable forecast of what's happening here. So I'm not going to keep my solution. I'm just going to keep this on the side and I'm going to show us a couple of things. So here it has told me that my optimum DI value is 0.00507. And then my optimum B is 2.04. Amazing. Now there's a simple problem here. And the problem is that a B of 2.04 tells me what about my decline? Is that realistic? Is that mathematically correct? Because I know from the physics and the engineering of decline curve analysis that I'm either going to be working with my exponential decline rate with B of 0, my hyperbolic decline with B of between 0 and 1, or my harmonic decline of B of 1. So a B of 2 is not very realistic. And so in that case, I can decide, scrap what I tried to do before. Let me redo my optimization. But in this case, I'm not going to change my B. I'm going to leave my B as it is, and then I'm only going to change my D value. And so when I do that, I click on solve again, and then try to see what comes out of it. And in this case, it gave me a good solution as well. Slightly higher error or sum of errors, but good solution nonetheless. And I kept my realistic value of B at 0.8, right? Now that was defined by me. How sure am I that my B is actually 0.8? So I'm going to say, okay, scrap that. I'm just going to go to exponential and work with just exponential and say my B is going to be 0 and run my solver and solve it. With solver now, I have gotten another solution, but with a much higher sum of errors across my data. And so that means maybe I wasn't very correct about keeping my B at 0. Maybe it might not actually be an exponential decline. Maybe it might actually be a hyperbolic or a harmonic decline. And the truth is that in reality, it can be a one-size-fits-all situation. Really, you can have different decline scenarios going on with your data. You just have to, as an engineer, you have to be sensitive enough to your data to know what is happening at different points where you're having changes, where you're having phase changes. But we are not trying to look at the phase changes here. We're not trying to look at changes here because that's going to just elongate or make our time um, go longer. We're trying to close this out um, before 8:30. So in that case, what I'm going to do is I'm going to tell myself, is there a way for me to keep my B in a reasonable region while getting a good solution? And thankfully, Solver helps us do that. As a matter of fact, the whole concept of optimization helps us do that by defining constraints. And in this case, we're going to define our constraints as B should be between 0 and 1. And I'm just going to come here and click on add. Now, in this case, what's going to happen is I'm going to change two variable cells, the D and the B. But in this case, my D can change anyhow it wants to change. I'm pretty confident that it's going to remain within a good scope. But my B, I want it to remain within the correct scope according to what I know. So I'm going to click on add here, and my cell reference is going to be my constraint is going to be that this should be less than or equal to 1, and this should be greater than or equal to 0. So when you come here, there's nothing like between. So I'm going to have to define two constraints for B. So I'm going to define the first constraint, B should be greater than or equal to 0. And then B should be less than or equal to 1. And I click OK. And so in that case, my constraints have been defined for B. And so by changing my variable cell B, I should still be able to have a reasonable result. So let's check it out. And finally, my solution has been obtained. And when I click OK on this, I see that, oh, it's actually a harmonic decline here. Perfectly 1.0, or that is the optimum case for me. And so I can trust my solution here, and I can use this solution um to make forecasts. Okay. And so that's how you can use solver to curve fit. The whole idea of using solver to curve fit is, how can I minimize errors? And so you see here that my error at 382 is much smaller than my error that I got before, 500 and something, when I was assuming exponential decline. Okay. This is dummy data. Really, this is really dummy data. But this is a good demonstration to show how decline curve, how curve fitting can work on DCA. So before I proceed to work on the EUR, the reserves, and MP, I would like to get feedback, see if I can get some questions for some people. I don't know if that's okay, Gerald, just to get people,
Yes,
yeah,
ready hands coming up.
okay,
Legide, please go ahead.
okay, okay, yeah,
Okay, good
please ask your
evening,
question.
and thank you for the explanation so far. I have two questions. The first question is how you got the number of days. I heard you say you use the crude method to get the number of days. Is there a way we can also learn the crude method or a different method? And then
Sorry, number of
also
what?
number of days.
Oh, okay, yeah, continue.
Okay, and then you kept on saying, okay, we need to get a good solution by defining constraints and all the adjustments you made. So I wanted to ask, what exactly makes a good solution? Is it lower number of errors, or like what exactly are we looking to see to know that this is a good solution? And if we are, let's say we tried the trial and error initially, the way you were assuming values for the B, and there's a chance that you got a very, very low amount of errors as opposed to when you define the constraints on the solver. Would it be ideal to pick that one with lower amount of constraints, or you just go with what the solver gives you after you have defined the constraints? Thank you.
Okay, yeah, too cool. Thank you. Very good questions. So the crude method, paying attention, don't worry, it was just me doing this minus that. It's not really there's really no special thing that should be done there. It's just for me to get the number of days between X and Y. To get that, you just do a little bit of subtraction. That's what I meant there. And then your second question, which is more important. Now, remember, the concept of optimization is changing things until you get a very good, a reliable solution. And a reliable solution is a solution that does not deviate as much from your actual reality. Okay. And the only way you can know how something deviates a lot from your actual reality is by performing a form of error analysis. There are different ways to run errors. There's root mean square error, there's absolute error, there's MSC, there's MAE. There are many error metrics that people use. Any error metric that is suitable for you in a particular situation as an engineer can be used to define what your best solution is. And so if you, in your trial and error method, you're tweaking by yourself, you're tweaking B or D or whatever by yourself without going to solver, and you get a solution that is even better than what solver could have given you, of course you should go with your solution, because um, what we're trying to do is we're trying to minimize errors. And once you have a minimum error, then you are good. it's unlikely that with your tweaking and tweaking, you're going to get something lower than or something better than what Solver will give you. And that's why Solver as a tool is there, is available for you. But, what you should have in your mind is that I'm just trying to minimize errors. I have my error metric that I'm looking at. Whatever solution, when I say solution, I mean your unknowns, the root of the equations, that's B and D. Whatever solution gives me the best um the best mimicry of reality is what I would go with. Whatever solution gives me the lowest error is what I would go with. Whether it comes from solver, it comes from you. I hope that answers your questions.
Yes, it does. Thank you very much.
Okay. So do I have any other questions? Okay. Seems it seems I can continue. I think okay. It means I have everybody with me here. Okay. So now that I have defined this, now that I have defined my decline, my decline rates, I know how my production is faring as time goes on. I can now start to estimate my reserves. And your reserves are basically what you have right there that you want to go and carry. So as you have produced, you have produced, you have produced, you have produced and gone. What is there left for you to carry is what makes up your reserves. And your reserves is basically the cumulative within this period that you have forecasted. And then your ultimate your EUR is basically, everything from what you have produced to the point where you're going to get to your economic limits. In this case, we have not defined our economic limits. So I hope I have time to just play around for us to define our economic limits. Let's say our economic limit is 300. Okay, so back to my slide. Sorry, I want to get a formula here. So back to my slide. I have these equations that help me define my cumulative production within a period, given 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 the initial production, and the production at the final time. So I have QI, I have QO, I have D, I have NP, I also have B. So what I'm going to do is I'm going to go into my VBA again, and I'm going to define my user-defined function to obtain, to call these cumulative functions whenever I need to run my cumulative. So I'll just go back in there. Come on. Something is wrong. I'm so sorry. Can you guys still hear me?
Yes, yes, I can hear you. Sorry.
Okay. Can you see anything on my screen?
No, it's blacked out now. It's back.
Okay. Okay. one of a software ran into a problem and it's nearly crashed the whole system. So it's back now. Okay, so create my user-defined function for cumulative production. Pretty simple, kind of like the first one. And in my module or anywhere, particularly, I can define multiple functions. So I'm just going to say function comprod. So let me put this as capital letter as well. Comprod, and then cumulative production. VBA and errors. Now the parameters for cumulative production are kind of the same thing as these other parameters that I used here. Or the arguments are the same thing as these other arguments. So I'm just going to place that in there. Now at this point, all I'm doing is just basic Excel sum, subtract, and the likes. Okay. So if B is equal to I is equal to 1, then my cumulative production, let me tab this, is equal to, what's happening? Okay, it's equal to QI over DI times ln QI over QO. Okay, QI over DI times of QI over Q. Okay. Okay, so now that means that there's another argument that needs to be here, which is Q. I don't think I even need C. Do I need C? I don't think I need C. Yeah, I don't need C. Okay, so if that's then else, my comp rod is equal to, so I need to be very careful here. So I'm going to use what we call worksheet functions for power. And the reason is because whenever this power symbol or this power sign comes before is used improperly, we might start running into errors. So I'm just going to use this opportunity to also mention worksheet functions. And worksheet function basically is a functionality in VBA that allows you to call actual Excel functions in VBA to make things easier for you to work. So I'm just going to say worksheets function dot power. I think is Q raised to power B. So that's QI raised to power B. I think I should be right.
Sorry, we
Yeah.
cannot see that. We can't
Can
see
you
what
see?
you're doing.
Can
So
you
you
see?
may need
Oh,
to reshare your
okay.
the entire screen.
Okay. Oh,
Yeah,
okay. Okay. I think I know
yeah.
what's up. Are you good now?
No, still can't see it.
Okay.
It's probably a different window, so you I think you have to
Yep.
reshare your screen. Yeah.
Yep. Yep. Okay. So are we good now?
Yes. Yeah. But I can you try doing what you were doing before? We can't still see it.
Sorry. So I'm just going to go back to VBA. So can you see it?
Yes, we can see it now.
All right, cool. So I'm just going to continue what I'm typing, trying to get a function out here. Q over D would be the Q response. Q, okay. So this is over DI times 1 minus B. Okay. Times worksheet function. One minus B. I'm just trying to write the function that we have there minus worksheet function. Q comma 1 minus B. So I think that should be it. So I'm missing something here, so just okay, cool. Okay, so okay, what's happening? Please tell me if you can see my screen.
We can see the spreadsheet.
Okay, spreadsheet.
Yeah.
Okay, that's cool. Did you see the VBA screen while I was writing the rest of the function?
No, I don't think we did. No.
Okay, so I'm just going to show that again. So yeah, this is just the function right here. And I'm just going to put an end if here. Okay, so what I'm just going to do is really quickly, I'll come back here to my reserves. My reserves is, okay, so let me just give you my reserves. My reserve is going to be cumulative production. And then get my functions. Now, realistically, there is a chance that my Q, my DI at this point, my DI here is going to be different from the DI I have here, possibly. And so in that case, I'm going to calculate what I call the instantaneous decline at this point, at the point of my blind forecast, right? And then I would use that to determine my reserves. And so my QI here is going to be the production at these initial points. Let me start from this point. Okay. Let me start from here. Then my DI is going to be, first of all, let me just have this. Then my D is going to be this, obviously. And my Q is going to be my economic limits. And then I'm going to click OK. I have a value error there, so I'm just going to define economic limits. Let me say 200. Okay. What I didn't define is my instantaneous decline, so I'm just going to put my formula for that. I didn't bring in my formula here. But the formula for instantaneous decline at this point, where I have my blind forecast, is, I'm trying to get us to round up very quickly right now, is my DI, sorry, is equal to DI over 1 plus B times DI times, where are we? Here. Gonna close that bracket. And I have this. So now it has given me my actual value for my reserves, and my reserves in this case is at 495,000. Okay. And that is basically what I have left here to be produced. Now, I would like to mention that this data was really dummy data. And so some values that you see here might be unrealistic in the engineering sense, but what we have here, right, what we have been able to develop here is a good way of getting our decline constants set up, estimating our reserves, and then using our reserves that have been estimated to get our final EUR. Let's get our final EUR pretty straightforward. If I have my cumulative production so far, I'm just going to go with a straightforward method for this. Something just happened. Our cumulative production so far, I'm just going to get to the final point, which is 23,533, right? Go to this. Our EUR then becomes of this two. Our EUR then becomes the sum of our cumulative production so far and the reserves that we have estimated. Okay. So using our weird looking data, our poor man data, we have been able to run a little bit of, we've been able to play around a little bit with our reserves estimation, and then we can tell what our future probably holds for us and how we can define our strategies going forward. So far, I didn't imagine that we would spend this much time. We had two things to do. I was supposed to do a live dashboard development with us here. Unfortunately, we have gone way past time. So I'm just going to open the floor for some questions, and then we can call it a day and probably set up something else for us to look at some further analysis in terms of production and production technology, if that's fine. So yeah, thank you very much for having me. I would open the floor up to some questions now.
Okay, thank you very much, Israel, for that very wonderful presentation, and taking the participants through the idea of curve fitting and optimization with solver in very good detail. So as Israel would have shown, or as Israel has shown, and you probably have seen, this can actually be applied to a whole lot of other different workflows. That's one of the reasons why we selected this particular case study for curve fitting case, an optimization case, because that can be applied to a lot of different workflows. For instance, you have your PVT data matching where you want to match empirical correlations, like your standing, Glasso, Vasquez, Beggs, and the likes, to your corrected PVT data. There are also other ways to apply that. You can apply that in material balance analysis for matching historical pressure and production profiles. You've seen the application of that in the kind of analysis. You can apply that, in most cases where you require correlations, for vertical lift performance, where you have correlations that you want to match to, actual data, you can apply. Okay, Israel, you're breaking up if you were saying something. But basically, the idea is you can apply this to a whole lot of different scenarios. All you need to do is just basically rearrange your problem, depending on the kind of optimization problem you're solving. Rearrange your problem statement, redefine your objective function, and then follow the steps that Israel has shown, and then you'll be able to, carry out all those different workflows in Microsoft Excel. A very, very amazing tool, Excel solver, because we do a lot of optimization, obviously, as engineers in most of our workflows. And also, like Israel said, we had planned to show a bit more today. Unfortunately, obviously, we were trying to, go into the detail to explain each of the different steps in developing this curve fit, especially because it is going to be applied to your project for this week. So unfortunately, there's no time to cover the other things that we had in store for you today. But we can always arrange a second session if you are interested. We're supposed to do some analytics, with production performance dashboards as a second part of this session. But due to time, if you would, we'll leave that choice to you. So if you are interested, just let us know in the group chat, and we will gauge the responses and the level of interest. And depending on how many people are interested, we can schedule a second session to go over that. But yeah, just before we wrap up, I'd just like to open the floor for any more questions that you may have, either regarding what Israel has taught today, or maybe something around how it could be applied to some other area of interest. You can ask that question. So I'll just open the floor for any more questions that we have. Please, you can raise your hand or drop your question in the chat. We'll just read it out and answer the question. Okay, it seems there are no questions. So I'm guessing that Isa did a fantastic job then with the explanation.
Yeah.
So
Sorry, I don't have it.
Are you just a quick one before you continue your section?
Okay.
I was looking at from the feedback on the group. I was looking at if it's possible, if we can plead for more time, like another section. I'm just seeing some of the comment for additional sections. So from Excel for energy, we can see how we can organize another section basically on Excel Visual Basic Application, that is VB and macros, for another 1 hour, 30 minutes. But I won't mind if it's possible to run it 3 times for them, so that then the next one will just be on visualization, so that whenever they have a performance plot data, they can always use your visualization skills. I can speak to Samuel to also do that too, just to spice it, but it's going to be an odd time for them, so at least they have to sacrifice their timing to join this section. So I don't know how you can accommodate that to spice up your program from Excel for energy. If that works well, I don't need the students that are okay with that. If they're okay with that, they can just react to it. Then we can see how we can organize additional section for them. Israel, does that work well for you?
Yeah, I'm okay with that.
All right, no problem. Okay, so Jared, so it's just for you. The ball is on your court. So if you can accommodate us for another section for the guys.
Yeah, definitely we can do that. Probably
Okay.
maybe later on in the week or next week, depending on
Oh, that's good.
yeah, the feedback. So we will put up a poll in the WhatsApp group, and then yes, we'll use that to gauge your interest and also the timing that people would prefer for this session. And then also if you have any particular area that you may want us to also cover. So maybe using Excel, for a particular kind of
Now,
workflow or analytics that
for
you are
them,
interested in.
but that would be
You can
possible
also drop
to
that. We will
like
look at the
next
different
week.
ones available and,
So that would be
try and fit them
thank
into
you.
the next session or next few sessions that we'll be organizing for you. So all of that will be discussed in the group. A poll will be created. Christian will send that out, and then you can share your feedback, and we will use that to plan for the next session.
All right, thank you, Jared. Okay, that's fine. Thank you.
Okay. So I think since there are no further questions, okay. Legide, please go ahead.
Okay, thank you. I wanted to ask this live dashboard development that he talked about, is this something that we need to complete the task that we are expected to turn in, or
Sorry, I didn't get what you said. The
he
first thing
mentioned
you
that he
said.
was supposed to do a live dashboard development for us, like was supposed to teach us that today. So I
Yes.
was asking if we need that to be able to complete the task or not. So, you know.
No. That is not needed. It's an additional learning for you. Obviously, as a production engineer, one of the things that's useful for your analytics and optimization is developing dashboards that you can use to monitor and study production performance. So that was the reason why we decided to do that for you today. It's not necessarily required for your project. It's just an added learning that will be very beneficial for you, an added skill to have. The development of those dashboards for analytics.
Okay, thank you.
You're welcome. Any more questions before we end the session? Okay, as there are no questions, thank you all so much for joining. As you know, we have the review session tomorrow. So we look forward to seeing you there. We will, as usual, drop the guidance, on the times and then the groups for each of the different times that we have for you. So I look forward to seeing you all and having the discussion on the projects for production technology and well performance tomorrow.
Thank you very much, Cheryl.